First, let's look at the containers. There are three categories of containers. The first one is sequence containers. Array and linked list are sequence containers. STL library provides vector, deck, list, forward list, and array. Second one is associative containers, which is typically implemented with binary tree. The key attribute of associative container is all the elements are always sorted. STL provides set, multi-set, map, multi-map. Last one is unordered containers, which is basically the hash table. And STL provides unordered set, multi-set, and unordered map, multi-map. It looks like a lot of containers, but don't worry, many of them are quite similar, as you will see. In order to use STL library, you have to include the corresponding headers. The header names are quite self-explanatory: vector, deck, list. The only thing is the set includes both set and multi-set, map includes both map and multi-map, and same thing for unordered set and unordered map. Iterator includes the iterator related things. Algorithm includes most of the algorithms, but there are some numeric algorithms are included in the numeric header. Functional for the functors. These are the headers that are used by my examples. Every time you see a compile error saying undefined containers or undefined functions, come back and to see if you have included the header. Let's first look at the sequence containers. We've already seen vector. A vector is a dynamic array that grows in one direction. Let's look at some examples. Vector has a member function called size, which returns the number of elements in the vector. So when I create a vector through its default constructor, vec.size is 0. Then I push back 418. Vec contains 418 and vec.size becomes 3. Vector's elements can be randomly accessed. So vec2 is 8 and vec.add2 is also 8. The only difference between these two ways of random accessing is the first one has no range check, and the second one throws range error exception when the index is out of the range. Because of the random accessness, I can traverse a vector just like traversing a native C++ array, like this. However, the recommended way of traversing a vector is through the iterator. For iter equal to rec.begin, iter not equal to rec.end, ++ iter. The reason is, number one, this way of traversing is usually faster than using random access. And number two, this is a universal way of traversing a container. So any container can be traversed like this. If I change vector to a list, this code is still valid. And lastly, C++ 11 provides a new way of traversing a container. One unique thing about vector is a dynamically allocated contiguous array in memory. None of other container provides contiguous data in memory. So for vector, if I create an integer pointer p which points to the first element of a vector, I can use p just like using a regular array. For example, I can do p2 equal to 6. The three groups of containers are very different from each other, but they are all containers, so they share some common interfaces. And here are some examples of the common APIs that are provided by all containers. Empty. Check if the container is empty or not. In this case, apparently not. Size returns the number of elements in the container. In this case, it's 3. Copy constructor. vec2 now have the same items as in vec, 418. Clear removes all the items in the container. Now vec.size becomes 0. vec2.swap_vec. This swaps the content between two containers. Now vec2 becomes empty and vec got the 3 items back. Since the containers have common APIs, you may expect there are some inheritance and polymorphism involved, which will bring some performance penalty of abstraction. Actually not. STL is very efficient. All the penalty of abstraction has been optimized away. It can run as fast as a well-crafted C program. This is one big reason why you should use STL. Properties of vector. First, fast insert and remove at the end of the vector. However, insert and remove at the beginning or in the middle of the vector is very slow. If you insert an item at the beginning or in the middle of a vector, all the items after that item have to be shifted toward the end. That is very slow. It takes linear time. And same thing happens when you remove an item in the beginning or in the middle. Number 3, slow search. Search also takes linear time. Now let's look at deck. Deck and vector have very similar interfaces. The biggest difference between these two is vector can only grow at the end of the vector, and deck can grow both at the end and at the beginning. Here I created a deck of integer that has 4, 6, 7. When I push front 2, 2 is inserted in the beginning of the deck. And when I push back 3, 3 is appended at the end. Although the underlying implementation of deck doesn't provide contiguous data, deck also provides random access just like a vector. So deck 1 is the element of 4. Properties of deck. Fast insert and remove at the beginning and at the end. Insert and remove in the middle is still slow. And search in a deck takes linear time, which is also slow. Now let's look at a list. A list is a doubly linked list. Each item inside the list has one pointer pointing to the item in the front and another pointer pointing to an item in the behind. The key attribute of a list is you have fast insert and remove at any place inside the list, not just in the front or in the back. Here I have a list of integer that has 5, 2, 9. And just like a deck, push back will put the item in the end, and push front will insert the item in the beginning. Then I use the algorithm function find to find the item of 2. Now iter is pointing to 2. Then I insert an element of 8 in front of iter. So 8 is inserted in front of 2. This is a very fast insertion. It only takes constant time, much faster than vector or deck. Then I increment the iter. Iter points to 9. I erase the iter. 9 is erased. And the erasure also takes constant time, very fast. So the property of a list is fast insert and remove at any place. But it also has slow search, linear time. You may say, yeah, as slow as vector. No, this is much slower than vector. Why? Because of locality. The computation bottleneck of a modern processor is dominated by memory access. That is why they have caches. As we said, vector stores data in a contiguous chunk of memory, which means when you swap that chunk of memory into cache, it is more likely that you'll use everything in the cache, or you'll get lots of cache hits. So cache loves contiguous memory of data. On the other hand, each element of a list is stored in different place in the memory. So when you traverse a list, you'll get a lot of cache misses. You end up swapping data in and out of the cache all the time, which will dramatically slow down your program. Many STL implementation has optimized the list such that the data in the memory is clustered together. But even in that case, since each element of a list contains two more pointers, so a list will consume more memory than a corresponding vector. And more memory means more cache misses and more page faults. So list in general is slower. And lastly, list doesn't have random access. Despite these drawbacks, list has one killing function that nobody else can match, which is splice. Here I have a mylist2, and it A and it B defines a range of data in mylist2. And with the splice function, I can cut this range of data from mylist2 and insert it into mylist1 at the position of iter. And this only takes constant time, no matter how huge this chunk of data is. This is a very big advantage, and none of the other containers can do that. Some people use list just for this purpose. So these are the things that you need to consider before you start using list. A forward list is just like a list, except that it only has forward pointer. So you can only traverse it from beginning to the end, not from the end to the beginning. Now what about arrays? If I have an array of integer that has 3, 4, 5, and I want to use all the convenient function of a.begin, a.end, a.size, a.swap, I can't do it. STL provides a solution. It's called array container. Array container is a very thin layer around the native array. It can be created with the element type and a size. There are two big limitations about the container array, which is number one, the size cannot be changed. Number two array of integer may have different type. So for example, I have another array which has 4 items called B, and A and B actually are different type. So if I have a function that takes an array of 3 elements, it won't take an array of 4 elements because they are different types. So these are the two limitations about the array. That's all for today. Thank you for watching. Feel free to subscribe to my channel so when I post a new video, you will be updated. Or you can go to my channel's homepage and see what I'm offering today. Bye bye.